This video is a walkthrough of the physics derivation graph. Today's date is March 20th of 2020. I'm on my Mac in a terminal and I have my uh, directory checked out here. I'm in the version 7 Pickle web interface and I'm in the web directory. So if I look at what the files are that really matter, it's primarily the Docker file and then compute.py and controller.py. So these are sort of like the workhorses. And then all the web pages hang out in this templates directory. All right, so I'm going to switch over to my other terminal and run a few commands. So I'm going to run python create temp.py docker build the Flask Ubuntu image. And then once I've got that, I'm going to run that image and publish port 5000 to 5000 on the host. So let's take a look at what that create temp.dby file is before we run that. So let's look at it. Create temp.dby. All right, so this is a Python file, and basically what it contains is a starting point for all of the content in the physics derivation graph. So this is eventually going to get overwritten with whatever else we sort of put in, because this Python script produces a JSON file, and the JSON file contains all the content. But this is just sort of an initialization of that database so that we have some content. So I'll walk through these data structures a little bit more, but primarily there's a variable called DAT, which has a bunch of keys, and the keys are expressions and inference rules, and then derivations, and then a relational table between the local expression ID and the global ID, the symbols used in the derivation graph, measures, units, and operators. So those are the main sort of tables in this JSON file. All right, so now that we've looked at that, let's go run our Docker file. So it's going to create that JSON file and then run the two docker build, docker run commands. And once that's up and running, it'll be available on my web browser in port 5000. So this is basically saying that the service is now available. And we can see there's a bit of output here with the trace. Those are print statements coming from the Python script in controller.py. Okay, so I happen to have my web browser open to that localhost 5000, and there's a web page with some options here. So the first thing that we can do is sort of click on the download the current database file. That'll give us a pop-up to the data.json that was written. This will become handy later on after we've made some edits to the derivation. We want to download that file again and get it out of the database. All right, so that's always available. And then let's look at the sort of like from the very basics, the operators and symbols. So first we'll look at all the symbols. This isn't very pretty currently, but the operators are sort of things like you'd expect, like addition, integration, division. Those are the things that take arguments. Symbols, also sort of what you'd expect. The symbols like X and Y and Z and A and B, all of these are sort of listed here. And so they each have some LaTeX representation, and then they have a numeric ID associated with each of them. So there's a unique numeric ID per symbol, and so that means that you could have different representations of the same variable in different languages. So what we care about right now is the symbol ID. So this symbol here, A, it's a variable I happen to like to use quite a bit, and so that variable ID is used in different expressions, and here we see a list of the expressions of where it's used. Each expression, as we'll see shortly, has its own unique identifier. So this is the relation between the symbol ID and the expressions in which that symbol is used. Okay, if we look at the expressions, that's sort of building up from the base. Each expression, as I mentioned, has an ID associated with it, and then there's some LaTeX representation. So let's say this is the formula we care about. And this LaTeX can be broken into an abstract syntax tree representation, here a list of lists. And then we can say where that expression is used. So it's used in the fun derivation, and in contrast, say this expression is used in another derivation over here. All right, so there's an options. We'll come back to these, but actually we'll do them right now. So let's look at so let's say this expression ID, that's one of two that is not used in any derivation. So that means we can delete it. It's available for deletion because it's not referenced anywhere in any derivation. So we can delete that. And then I can also say I want to edit this expression ID. I can change what the length of what the LaTeX is. Alright, so there you saw the LaTeX change. Alright, so there we deleted an expression and we edited an expression. If we look at the inference rules, the sort of layout is pretty similar in the sense of every inference rule has a name, some number of inputs and outputs and feeds, and then a LaTeX expression that goes with it. Now most of these currently are not used, but this one here, add x to both sides, is currently used in fun derivation. Okay, so all those options are there. Alright, so if we want to view existing derivations, this is sort of like the showing off what we have so far from that preloaded data.json. We can either display a GraphViz file. Let's take a look at what that looks like. So here we have the GraphViz output of the derivation, as well as a table of all the steps. So even though this graph here is unordered, in that you just have directionality in the graph, there are linear steps, linear indices here for each step. And the reason for that is if we generate a PDF, the linearization requires some ordering. So for instance, I want equation 1 to always show up first, and this is the initial condition. So here we can see that edit that we made. So we made an edit to the LaTeX, and that didn't get reflected, that change didn't get reflected in the expression. So there's some lack of validation check here. We'll talk about validation later. But this is sort of the input to that PDF format. So if we wanted to correct that, let's say we want to go back and we know that that is wrong, so we want to change it back to K. So let's do that. All expressions, and then so this one here really should be K. So I'm going to change that to K. All right, so now let's go take a look at that derivation again. And I believe that was the fun derivation. So that looks more correct. So now we can add both sides to that, a equals b, and get a plus k equals b equals k. And then we can check that the PDF also reflects that change. So that looks much better. All right. Now let's make a new derivation. That's sort of more exciting. So let's an example. All right, so we'll name our derivation, and we're gonna start by creating a new derivation, and the input will be b equals j. All right, so I'm starting out with a new expression that doesn't exist anywhere, and currently in this table here only has a header because currently there are no steps. We're in a new derivation. Okay, so there's my preview. I like what I see here. So I'm going to accept this step and add another step. And then this time I'm going to do add x to both sides. So this time I already have an existing expression that I want to start from. So I'm going to use the expression ID. And then I'm going to add, say, the number 2 to both sides. And then my output expression would be b plus 2 equals g plus 2. All right. So the sort of exciting thing here is not only do I get a visualization of what that step looks like, I also get that the step is valid. And that was because in the background, Sympy read the LaTeX expression here and here and here, and then validated that when you apply this rule to those inputs and the feed, that you really do get that output. So this statement right here is coming from Sympy reading the LaTeX. So now let's take a look at what that derivation looks like in whole. Okay, so the ordering is declare initial expression, b equals g, add 2 to both sides, and we get b plus 2 equals g plus 2. All right, we'll add one more step and then take a look at the PDF. So here we're going to declare final expression, and this is my last expression, so let's do that. All right, that looks correct. So now we'll review the derivation. And that looks pretty right, so let's look at generate PDF. All right, so there is our derivation. Yeah. So there's a lot of things that are not currently working yet, but we'll make new videos as new features are added.